Okay, let's dive into this. You've almost certainly heard of Newton's second law, right? F equals ma? It's like physics 101. But what if I told you that famous law has a spinning twin, a kind of secret identity that explains how everything from a tiny toy top to a massive galaxy rotates?
I mean, think about it for a second. You've probably never even questioned it, but why is it there? Have you ever tried pushing a door open right next to the hinges? It's practically impossible, right? You're still pushing with the same force, so what gives? This super simple question, it actually gets us right to the heart of what we're talking about today. And that right there is the key. It's not just about how hard you push, it's about the twisting effect that push creates. And in physics, that twisting effect has a name, and it is the first piece of the puzzle for understanding Newton's law for things that spin.
So let's make it official. We are going to break down the direct counterpart to Newton's second law, but for rotational motion. And the cool thing is, the analogy between the two is so clean, so perfect, that it makes these complex spinning systems feel surprisingly easy to understand.
Okay, check this out. It's so elegant. On the left, our old friend F equals ma. On the right, its rotational twin. You can see how each part has a perfect parallel. Force, F, gets swapped out for something called torque. That's the Greek letter tau. Mass, m, gets replaced by a new concept called moment of inertia, or I. And finally, regular linear acceleration, a, is replaced by angular acceleration, alpha. So let's meet these new characters, one by one.
All right, first up is the rotational version of force, torque. This is the big idea that finally answers our door handle question.
So what is torque, really? Well, in the simplest terms, it's the thing that makes stuff spin, or stop spinning, or change how fast it's spinning. You know how a force causes an object to change its linear motion? Well, a torque causes an object to change its rotational motion. It's as simple as that.
This diagram is awesome because it shows exactly how it all adds up. Just like you can have a net force, you can have a net torque. Here, you've got three different forces pushing at different distances from the center. The total twist is just the sum of all the individual twists. See how F1 and F2 are trying to spin it one way, while F3 is fighting back, trying to spin it the other way? It's like a rotational tug-of-war. And just a little heads up, physicists usually call counterclockwise torques positive and clockwise ones negative. Okay, so if torque is the rotational push, what's the resistance? What pushes back? Well, that brings us to the rotational version of mass, the moment of inertia.
Think of it this way. If mass is how stubborn an object is about changing its motion in a straight line, then moment of inertia is how stubborn it is about changing its spin. Something with a huge moment of inertia is really hard to get spinning, and once it's going, it's really hard to stop. But, and this is a big but, there's a huge difference between mass and moment of inertia.
And this is the kicker. An object doesn't just have one moment of inertia. Its value completely changes depending on where you try to spin it from. See, mass is just mass. A 10-kilogram ball is always a 10-kilogram ball. But its moment of inertia, that depends on the pivot point. Let me show you what I mean. All right, take a look at this system. We've got three masses, m, 2m, and 3m, all connected by some lightweight rods. Now, the big question is, how hard is it to get this whole contraption spinning? Well, the answer is, it depends. It depends on whether we try to spin it around point A or around point B. And wow, the numbers really don't lie. When you do the calculation, which is just summing up each mass times the square of its distance from the pivot, look what happens. If we spin it around axis A, we get a moment of inertia of 14 ml squared. But if we pivot it around the middle mass, B, it's only 4 ml squared. It is more than 3 times harder to spin this thing around point A, all because more of the mass is spread out farther away. For more complicated shapes, there are even fancier tricks, like the parallel axis theorem, to figure this out. So we see that where you spin something from is just as important as what you're spinning. Okay, awesome. We now have our two key ingredients, torque and momentum of inertia. Now we get to do the fun part. Put our new formula, tau equals I alpha, to work and solve a classic physics problem.
So here's the scene. You've got this big, heavy drum that can spin on an axle. A rope is wrapped around it, and hanging from that rope is a 10-kilogram block. We let go of the block, it falls, the rope unwinds, and the drum starts to spin. Our mission? Figure out exactly how quickly that drum accelerates its spin.
Now, to tackle this, we have to be smart. We've actually got two things happening at once, so we need to analyze them separately.
For the block that's falling, that's a linear motion problem. It's got weight pulling it down and tension from the rope pulling it up. That's a job for our old friend F equals ma. But for the drum, that's a rotational motion problem. The only thing making it spin is the torque from the rope tension, and that's a job for our new tool, tau equals I alpha.
So here's our three-step attack plan. Step 1, we look at the block, use Newton's second law, and we get an equation. Step 2, we look at the drum, use our new rotational law, and we get another equation. And then step 3, this is the magic link, we connect them. Because the rope doesn't slip, the speed of the block is tied directly to the speed of the drum's rotation. That gives us our third equation, A is equal to R alpha, and lets us solve the whole thing.
And after we do all the algebra, combine those equations and plug in the numbers, we get our answer. The angular acceleration of the drum is 2.706 radians per second squared. Boom! We've successfully used the rotational version of Newton's law to predict exactly how this system will behave.
Okay, that was a pretty cool problem. But you might be wondering, why does this matter outside of a physics class? Well, it matters a lot.
Because this idea extends one of the universe's most fundamental rules to a whole new world of motion. This is the principle that governs pretty much anything that rotates. We're talking about the tiny gears in a watch, the giant wheels on a train, even the orbits of planets. This is what engineers use to design powerful engines and massive wind turbines. And honestly, once you get the hang of the simple analogy between the linear and the rotational, problems that seemed super complicated suddenly start to just make sense.
And that leaves us with one final, really interesting question to chew on. We've established that if you apply a net torque to something, its rotation will change. So what happens if something is already spinning? Think of a figure skater in a twirl, and suddenly the net torque on them drops to 0. What happens to their spin then? Well, that question leads us directly to another giant idea in physics, the conservation of angular momentum.